So let's continue in 6.1. This is on the more general method of solids of revolution called the washer method. So let's take a look at that. So above here, this is what we did for the disk method. So basically you're taking a bunch of little cylinders in here and then you're adding them up. Here's the next one and then here's the next one. And so this method looks like this. So what if you had a solid of revolution that looks like this? So give me a second. Okay. So suppose you have two functions, say like this. So draw an x and y. So then suppose you have a function f of x, say here, and your g of x, say, I don't like that one. Let's try a different way. Say here, okay, a little better. So this is your f of x, and this is your g of x function. And you want to go from A to B, like that. So this is the region in question, like that. Well, between those two curves. So the region in question we're going to look at would be this. So we're going to take this region here. Oops, I want to do that. And we're going to revolve that around the x-axis. So we're taking that. So we want to go, we take our little representative rectangle. So you go up like that and like that, just like we did before. We're going to take that now and revolve it. So we're going to revolve that around the x-axis. I didn't really like how I drew that. I'm trying to do that a little better. So you revolve that around the x-axis like that. But then if you do that, you get an inside little thing. So what you end up getting, and is to try and draw like another one like this. Okay, and it goes like that, right? It just kind of goes up. Then you have another one in here. So what does that look like? Doesn't that look like a washer? Yeah, that's where it comes from. That's just like, so in class, what I would do is I have these little washers, like a bunch of them, different sizes, right? And if you stack them vertically like that, like this, then you can see different size washers are going to create this solid. So you got to picture that solid being revolved around. So this is another picture of what it would look like from the book or a book. I don't know if it's our book. I forget. So, and I like how on theirs, or don't like how on theirs, they don't use the representative like washer. So it should look like that. So it has thickness to it, not just a line. It's got thickness because that thickness is really important of how you know whether it's dx or dy. So that thickness is a delta x. Everything's in terms of x. And so the thickness is delta x. Okay, when you go around like that. So the volume then is pretty straightforward. I mean, basically the volume is similar to before. You have an inside and an outside. So you take the volume of the large one as if G wasn't there. So volume of the large minus the small. So so it's like you're using the disk method that's above, and then you're just taking the large one, whatever that would be up here. So that's this whole thing. And then you subtract off this one. You subtract off G, and that would give you what's left over. Okay, so picture that again. So you take the largest one, so it's the whole thing, and then you subtract off this piece down here. And that's what's left. So you get volume is equal to, basically it's the sum of the large one. So it's going to be pi f of x squared minus the sum of the smaller one, which is g of x squared. Oops, and what did I forget? I forgot the delta x. Yeah, I forgot the delta x right there. We'll fit it in there here. So this is your delta x. Delta x. Okay, so once you take a limit, right? So this is a volume approximation. Once you do a limit, so take the limit, you break it up just as before. Limit, norm of the partition approaches 0, etc., all that good stuff. Partition AB, and you get that the volume is the larger one, which is a to b, pi f of x squared dx minus the smaller one, a to b, pi, g of x, g of x squared dx. And then see what you can do is you basically do one integral and factor out the pi. So you're going to factor pi out of there. And you're going to do one integration going across. So you do one integration and you end up kind of with a formula. Again, I still want you to visualize what's going on, not just remember. You can't just memorize formulas at this point. So that's equal to pi, then the definite integral from a to b, and then it's f of x squared minus g of x squared dx. I'm just trying to get this in the right spot. So I'm just waste space, viewing space. Okay, so that's the basic idea. It's essentially the disk method, right? It's just you're just using the disk method twice. It's like you're just taking this one up here, and I'm going to erase it in a second, but you're taking this one up here and doing a large one, which we know, and then you take, what if you have another one in here? And then now you really just want to find this. So then you just take the large one, like that, and then you subtract off the small one, and you get what's left, which is this. Right, so that's what you're doing. Let's look at an example. Okay, I'm going to go ahead and shrink this a little bit. Oops, not that. Put that a little smaller so we can fit everything in here. All right, so take a look at this one. So the region bounded by the graphs of, so let's write that out, the region bounded by the graphs of y equal to x squared plus 2. So that's the same as above, right? And this time we're doing 2y minus x minus 2 equal to 0, x equal to 0, and x equal to 1 is revolved about the x-axis or around the x-axis. Find the volume of the resulting solid. Okay. So first, let's just do a little work ahead of time. We know we're going to need to graph this 2y minus x minus 2 equals 0. So let's put that in slope-intercept form. So that's 2y equal to x plus 2. So we know that's y equal to 1/2 x plus 1. We're going to need to do that. There's a little preliminary work ahead of time. All right, so then let's go ahead and, so what's next? What do you need to do next? We need to graph. Yeah, I need to graph everything. So we need to graph the regions. So let's see. So we have our parabola just as before. Like that. And then, oh, and then notice I already put in there, it's from 0 to 1. So it's really just this piece right here that we're talking about. But we have another line that's going to come through here. So you're up. Oh, that's a 2. Okay. Let's do this. Well, that's all right. We'll just keep it. I'll zoom in. So this is 2 here. And then so this is 1. So it's just that little piece, really. Probably want to do this to not to scale. So I'm going to do it a little differently. We're going to come up. So this would be 2. And we're just going to go for it like that. And then we're going to graph from here. So up at 1, you're at, so this is up 1 over 1, 2. So the graph, this other graph's coming in like this. That's still off a little bit, but it's not going to go down there, so you don't really care about that. So there's your 1 line, and then you're going to be breaking it off here at 1. So just like this. So this is the region that's being revolved right here. That region right there is what's being revolved around the x-axis. So let me clean that up a little bit. This is what math people do. We're very careful about things, aren't we? Okay, so I'm cleaning that up. You can fast forward. I realized, did I say this already? I don't forget. You can go at like double speed and stuff. It's kind of cool. All right, so that's being revolved. So we're going to take a little rectangle in here like this, and then we're going to picture that those are little wafers, little cylinders, but they're washers. The washers are going to be revolved around. So I like to do this like this. It actually works better because I can do it all in one stroke, right? So you got that going, and you got this going. So there's your washer method you're going to use. You don't need to go farther than that because it's hard to draw, hard to picture that. So let's, we're going to call this my delta x. My height here is my f function is the parabola. So we're going to say f of x is the x squared plus 2. And then we know my g of x is then the 1/2 x plus 1. And so now we kind of have, we have a formula, yes, but we can picture what we're going to be doing. We're going to be taking this whole thing here and then subtracting off this here. And it's those cylinders that we're subtracting off. So take this entire cylinder here, and then we're going to subtract off that inside cylinder. Okay, so what you get then is you get the volume of the washer. Let's do it like this first. The volume of the washer is pi r squared minus pi little r squared times the thickness times your delta x. So actually, you know what? I think I did that in class just to speed things up. What I really would want to show you first is something like this. Volume of the washer is a large, so it's the volume of the large minus the small. And so the large one is pi r squared times the thickness, so that's your delta x. Right? And then minus pi, then the smaller radius squared times your delta x. And then you can simplify that. So you can factor out the pi r squared minus little r squared and delta x. That becomes your dx. Okay, so now you do the limit. Norm of the partition approaches 0, etc. You don't have to show this stuff. I'm just want you to, if you picture in terms of summations, it'll make sense. If you try to do this in terms of formulas, it will not make as much sense. It's easier to get things wrong. So our volume after you do the summation is a limit, norm of the partition approaches 0, and then you're going to add up all those pieces. So it's pi, and then your large radius is f of x squared minus the smaller radius is your g of x squared, and then it's your delta x. Just do it all over the k's, so delta x sub k. And then that becomes your integral. So there's your integral. What are we integrating from where to where? What did it say? So you're going from x is 0 to x is 1, right? So here's your 1. But this is 1. Oops. Totally messed that up, huh? Okay, so here's your inside. This is your 1. You're adding it up from 0 to 1. So your integral is going to go from 0 to 1. All right, then you can factor out the pi. And then you have your f of x is x squared plus 2 quantity squared minus 1/2 x plus 1 quantity squared. And then your dx. Okay, so you want to multiply all that out. Okay, so multiply out and evaluate. And you should get 79 pi over 20. Or 79 pi 20ths, either way. Okay, so you multiply all that out, you'll get x to the 4th again, you'll get plus 2x squared again, plus 2. And then you evaluate from 0 to 1. So it'll just be a polynomial, so the 0 won't do a lot. That'll be nice. And the 1 will be simple as well. Okay, so check that. And as before, if you don't get that and you want to go over it, I'd be happy to go over it in a Zoom session with you. If you're looking at this well into the future and we have a class, then even better. We'll just have done it in class. So this right here, that's classwork. All right. What's next? Next, we're going to revolve about the y-axis and then a few more examples. It's a really long section, actually.